So, lesson 8. Remember, for parallel plates, first of all, you get the voltage. It's given by the battery that you hook it up to, so it'll be in the picture, usually. And it varies directly. And also recall we said this. We defined voltage as how much potential energy every coulomb of charge had. We defined voltage that way. That was the definition of voltage. And that inadvertently, Jake, gives us also another way to write potential energy. Potential energy is... I just got the PE by itself, times by Q. What this means is because the voltage between plates is just readable as opposed to between point charges where we had to calculate KQ over R, it gives us a very quick way to find potential energy and work. So example 1 says, find the work done by an external agent, an invisible angel, that moves a 2.5 microcoulomb charge from the negative to the positive. First of all, which way does this charge want to move? From positive to negative. This charge wants to fall down. Mathematically, Emma, this is the same as saying, find how much work it takes to lift something up. What you're really doing is you're saying, all you're doing is you're giving it potential energy. When you lift something, gravitational potential energy. In this question, because it's in an electric field and in a voltage, you're giving it electric potential energy. I'm going to do this the long formal way, and then I'm going to say, here's the short way to think about it. The long formal way is to say, well, it's work. And then to say, I think if we're starting at rest and ending at rest, because it says we can assume that, do that. And then say, what's changing anything? Final minus initial. You know what? I'm really now going to say, actually, I think it's going to be Q times the change in voltage. That has a built-in final minus initial because there's a delta in there. How big is the charge that we're moving? 2.5 microcoulombs. How many volts are we moving it through? What's its change in voltage? 120. There. And you get, can I do this in my head? Maybe. 2 times 120 is 240. Half of 120 is 60. 300. 3 times 10 to the negative 3? Negative 4. Decimal was wrong. 3.0 times 10 to the negative 4 joules. Now, you could do this the Physics 11 method. What was work in Physics 11? Work was what times what? Okay, so you could go they didn't tell me the distance, patience. Which force? Electric force. What did we say electric force was? Electric force was QE times D. Remember? What's E? Electric field. Hey, what was the electric field between plates? How did we calculate that? That was the other way to calculate electric field, Vanessa. It was change in voltage what happens, Atla? Which one's faster? That one, the bottom one. It's sitting on our formula sheet in disguise, because on your formula sheet it does not say potential energy equals Q change in voltage, but it does say change in voltage is potential energy divided by Q, and that's an easy one to rewrite in our head. But I did want to point out, This is one of the reasons plates are so nice. The force is constant. I can use my physics 11 stuff again if I really want to. But actually, it turns out it's not much faster. In fact, it's not faster. This is the same as lifting an object up. By the way, when you lift an object up and let go, what happens? I'm going to say it a different way. When you lift an object up and let go, what happens to the potential energy? It turns into kinetic energy. Now we can start to talk about firing particles, shooting particles, particle accelerators. Next page over. Example 2. Example 2. Alex, what does example 2 want me to find? Speed or velocity? Okay, which suggests a scalar approach. Maybe I can get there with a vector approach too, but when I see speed, they're picking their words carefully. What we're really saying is it's the same situation as we just did, tilted on its side. We have somehow lifted this charge up. This charge right here, what kind of charge? Electron. Electron, negative or positive? Negative. What's the voltage here? Negative or positive? So attracted or repelled? It's going to want to fall. Now, what we've really done is we've said, okay, imagine that you're lifting an object up and you're going to drop it, but you're also digging a hole so it can keep falling, except here's where the analogy breaks down. Once it gets into the hole and keeps falling, it's not going to accelerate anymore because there's no more energy. In real life, it would keep speeding up. Here, no. Okay? Find the final speed. We can do this as conservation of energy. Oh, and the reason it says there is no external agent, so system energy is conserved, there's nothing doing the work this time. This time it's just the natural processes. I think we're starting at rest. What's my initial potential energy? QV. The ground is right here. I know it keeps moving past the ground. This is, Emma, where my gravity analogy breaks down, but the ground is right there. When you hit the ground, what was your final potential energy? Ashley? Zero. So we can say, what we're really saying is, you know what? Once you leave the plates, you've used up all of the stored electrical energy. Sam, it's all been turned into kinetic. By the way, this is the equation that I warned you about low those many days ago that has a V and a V. This is why I started going to the big wings for voltage and no wings for speed or velocity. Otherwise, I was tempted to start to cancel things that can't cancel. Emma, we need more letters in our alphabet. Well, no, we don't. We'll work around it. Alex, what do you say we're trying to find? Oh, I guess it's going to be is that right? Times by 2, divide by m, square root. What's the last mathematical operation that we're doing? Square root. Can I take the square root of a negative? No. This is technically scalar. You know what? Because you're taking the square root of a negative using this, if you really want to, you can just say, forget the signs. But for what it's worth, the charge is negative and the voltage is negative. I have a negative times a negative, which is a positive. So I'll put them in, but you can be a little sloppy here. It's going to be 2. Q, charge. It's an electron. Negative 1.6 times 10 to the negative 19. V, voltage, negative 125. M, mass. It's an electron. All I know is it's 9.11, but I can never remember the times 10 to the negative 31. Okay, make sure you know it's on your formula sheet, right? How fast will we be going? One. Did I type that in right? Negative square root. 6.63 times 10. 1, 2, 3, 4, 5, 6. 6.63 times 10 to the 6th. It's going to be moving pretty fast. Oh, other stuff I could do, Sam? I guess if I gave you, for example, this distance, you could find the time. You could even find the average acceleration. Actually, because it's a constant force, it wouldn't even be an average acceleration. It would be the acceleration. Whatever. So, as we see in the above calculation, what we're really saying is when a particle is accelerated from rest, we have a simple energy equation. All of the potential becomes kinetic. We get QV equals a half mv final squared. We must take care in this equation not to confuse V with V. What if you're not at rest? Well, then up here, you'd have a half mv squared there as well, and you'd have to do a little bit more math and crunching of numbers before you got the other V by itself. Okay? So, suppose an electron is already moving at 5 times 10 to the 5th meters per second, and it enters a set of accelerating plates. Find its speed when it leaves the plates. Okay. This is sort of like a change in height, change. You know what? This is a job for speed conservation of energy. Are any of these 0? Is it starting at rest? Not this time. Here's where it's falling through, that's my analogy, the voltage. Is it ending up at rest? No. But once it leaves the plates, it no longer has any more potential energy. It's used it all up once it gets to there, because that's the ground. Okay. This is going to be a half mv initial squared plus, q v. That equals a half mv final squared. You know what? I think I can get the V by itself. I mean, I don't have to. You could, if you wanted to, crunch that, get an answer, times by 2, divide by m square root. But just for giggles, I think I'm going to go like this. Times by 2, times by 2, times by 2, because that gets rid of that, and that gets rid of that. And I get mv initial squared plus 2q change in voltage equals v final squared, divide by m. Square root. Now you'll notice, Kyle, I was a bit more careful here. First of all, I should have put wings on that V. I was a bit more careful here. I've been putting a delta in front of this. And the reason is the voltage 600? No, because where do we start at? What's the change in voltage? 500. I was a little sloppier on the previous one because there was a 0, so I really didn't bother putting a change in, even though it's always a change in. So now we should have kind of, I think, vaguely plug and chug. V should be M. It's an electron. Was it negative 31? V, what'd they say? 5 times 10 to the 5th squared. Plus 2. Need more room, Mr. Dueck. Well, let's write 1.6 times 10 to the negative 19. The change in voltage is 500 all over 9.11 times 10 to the negative 31 equals. Five, 7, 2, 1.6. That divided by 9.11. Oop, that would have been a problem. Square root. Do you get that? Or am I wrong? Now, by the way, Vanessa, if you also wanted to, again, you could have just crunched the whole left side, got an answer, because I've done a lot of number solving just because you know I'm a nerd, I like doing that. Double check, 9.11 to 10 to the negative 31. 5 times 10 to the 5th squared plus 2 times 1.6 times 10 to the negative 19 times 500, check. Divided by the mass, check. Square root. I think I'm right, am I not? I'm getting no feedback. Yes or yeah? Anybody else get that? Close. Is there an M in there? Then you cannot. So, when I used to teach Math 12, Atla, ask me the question again. Have you factored? That was always, anytime a kid said, can I cancel? My instant response, and I taught them this, have you factored the top? And if you can't factor a GCF out of the top, it isn't going to cancel. It's not going to cancel. Can I cancel? Have I factored? Those two questions always go together. Sorry, what? Oh. I got 1.33 times 1, 2, 3, 4, 5, 6, 7. 1.33 times 10 to the 7th. And it turns out we've just come very close to inventing TV. Well, first of all, the old black and white TVs, okay? The old black and white TVs were actually what were called a cathode ray tube, or a CRT, cathode ray tube. And it's a very, very simple idea. I'm going to draw a bigger version right here. Put your pencils down and look up. To design a TV, what you had here was some kind of electron gun. Now, how would you do that? What you would have is a plate here that was charged very, 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 very negatively. You would also have a negative plate here and a negative plate right here, so that any electrons that bled off from here would just get pushed to the middle and repelled. And what you would do is you would have a very, very small slit right there, so any electrons that don't go straight through the center in a horizontal line would just bounce off here anyways, and they wouldn't be part of your picture. So what you can do with that then is you can get, Logan, a very nice steady beam of electrons. Now, at the time, they called this a cathode ray because this was invented before they knew what electrons were. Then what? Well, what you have here is the TV screen, and you coat the inside of it with phosphorescent paint that will fluoresce, glow, when an electron hits it. This is why, if you've ever seen an old black and white TV, when you first turned it on, there was always a bright white dot right in the middle there. That was the electron beam hitting dead center. Because it took time for everything to warm up back then. So far, so good. What I want to do is figure out a way to, instead of having it hit dead center, maybe there's a way that I can have an electron hit right there and make a dot right there. And another dot right there, and leave this blank, but have another dot right there, and leave this, and have another dot right there, and do it so fast that your eye sees it as a picture. And you can. You have another set of plates. Right here. And right here, I'll make this one positive. I'll make this one negative. As this electron is traveling, right when it gets to the beginning of these plates, what direction will it feel a force? Up to there. Or, if you lower the voltage in those plates, to there. Lower the voltage a bit more, get hit there. Flip the voltage, because we do use alternating current, make the bottom plate positive. You can put an electron wherever you want. Then you have to imagine a third set of plates. I can't draw it because it's 3D. I'm going to try. The third set of plates would be right here. And you would have one positive side close to us. And then, this is Mr. Dueck attempting to draw 3D, one negative side away from us. And it turns out that these you wouldn't see the electrons. They'd be going between them. That lets you deflect it either towards me or away from me. So now not only can I move an electron beam up and down, I can move it left and right. On that TV screen that you see facing you, I can put an electron wherever you want it and make a little blip glow. Oh, and if I do several thousand electrons really fast, your brain will just automatically see a picture. The frame rate is 60 hertz. It goes, I think the way the old black and white TVs went is they went this way in a zigzag. So they would do top, go down, and they could refresh your screen 60 times a second. And that was enough for your brain to say, well, films are 24 frames a second. So 60 times a second was more than enough for your brain, instead of seeing separate pictures, to see moving pictures. That's it. We have what we call the accelerating plates. We have the deflecting plates. That was black and white TV. Oh, and the way that you manipulated the voltage in these deflecting plates is that's actually what you just, the nice thing was, the way a camera works. Light coming in to a camera hits another plate that's sensitive to voltage and changes its voltage. All you did was you sent that same voltage through the wires, you amplified it, but if you hooked it up to the TV, you automatically had the correct voltage to deflect things. You didn't have to do anything else. It just took care of itself. It's very nice. It's very nice. So, here's another picture. It says, describe the motion of an electron beam in a cathode ray tube. So an electron would start out at rest. Right here, this would be negatively charged. You could make this positively charged if you wanted to as well. In the picture that I gave you, I added a couple of more plates there to really push things to the middle. Traditionally, we don't bother drawing those in, but they're there. So I didn't add those to this picture. But an electron beam would come in a nice straight line. Perfect? No, that's why TVs were never the same as life. And also because you were lighting up little individual pixels. And then you can deflect it. Which way will this electron beam be deflected, up or down? Going to hit right there. Flip the voltage, it'll be deflected down. And this is a fluorescent screen. If you ever take apart an old black and white TV, on the inside of the screen, it's just a fluorescent paint. It's a paint that will glow when an electron hits it for a short little bit. It's very low tech, very clever, very low tech. I wrote describe the motion. We've just done it orally. By the way, McKinley, I fibbed. Actually, after setting it up this way, they came up with a better way to do the deflecting. It turns out, and we'll learn this towards the end of the year, you can also deflect the electrons with magnets, and the magnets can be built much smaller, so you don't have to have a long plate. But this explains why all of those old TVs had that big bulge sticking out the back. That was your electron gun. You needed that. It also explains why the older TVs had lousier picture quality on the edges. This is where you had some blurring. It was tougher to get it all the way deflected like that. So here's another picture as well. We have our cathode. Here's the focusing anode. This one does have the focusing anode to push everything to the middle. Here is plates deflecting it up and down. Here are plates deflecting it left and right. And it's going to hit the cathode ray. It's going to hit the fluorescent screen. This is a cathode ray tube. Put your pencils down. Look up. So, what are some questions I could ask you about the cathode ray? Well, A, find the speed of the electron beam after the electron gun. Okay. That's this section here. Did they say find velocity? No. Well, then I think this is just like dropping an object. It's going to be oh, and it does say VI is 0. And Jake, when I travel all the way through that 1200 volts, I've used up all of my potential energy. In fact, we can say Q, change in voltage, equals a half mv squared. QV equals a half mv squared. Don't get the v's confused. In fact, I think we're going to end up with what we had on the first page. If I get the v by itself, I saw Carly looking. I'm going to use my brain rather than look. I think it's going to be 2q big V over little m square root. Did I leave you lots of room? Okay, good, I did. Which is going to be the square root of 2q. It's an electron beam. 1.6 times 10 to the negative 19. V, 1200. M, oh, it's an electron. What was it? 9.11 times, was it negative 31? How fast are the electrons traveling? Oh. Divided by 9.11 square root. Answer. Do you get 2.05? That? 2.05 times 10 to the 1, 2, 3, 4, 5, 6, 7. Meters per second. Okay. Now they've left the accelerating voltage. Now they're into the deflecting area. What else could I ask you to find? Oh, what does B want me to find? The vertical acceleration. Oh. You know what? I think what they want me to do is this. MA. By the way, we're going to ignore the force of gravity on electrons because they're so light that basically gravity doesn't affect them anyways. But which force is deflecting them, is causing them to be deflected in this section here? Which force is that? I think it's the electric force. Now, what's the electric force? Don't write KQ, don't write this down, Q2. Oh, that's if you have two separate charges, but there was another equation that had an F in it. You have to rewrite it. Now, this is a vertical acceleration. Are there any horizontal forces acting on it in this section here? No. So horizontally, no acceleration. Vertically, hey, this almost sounds like sort of like projectiles and components. You can kind of think of it that way, but it's not gravity doing the work here, doing the deflecting or the accelerating. They want the acceleration. Okay. A is going to be QE over M. Oh, I don't know the electric field. Or do I? Can I figure out the electric field? It's going to be Q. It's going to be M on the bottom, but electric field between plates is the voltage divided by the distance. The acceleration, Q, it's an electron. Which voltage? The deflecting voltage, not the 1200, the 750. By the way, this is why TVs also took a lot of power. Mass, it's an electron. Which distance? The 0.02. How far apart they are, not the 5. All right, what's my deflecting acceleration? Is that right? Do you get that? 6.56? No, sorry, 6.59 times 10 to the 15th meters per second squared. What else could I ask you to find? Time to travel through the deflecting grid. Oh. You know what? It's going to be this. D equals VIT plus a half AT squared. Except, what did I say the horizontal acceleration was here? When you're going through the grid, when you're going through the deflecting plates, is there any horizontal force? So what's your acceleration horizontally? Get the T by itself. T is going to be distance divided by velocity. Which distance? The horizontal distance, which was how many centimeters? So 0.05. Which velocity? The answer from A. Right? That's how fast it's traveling through there. 2.05 times 10 to the 7th. It's going to not be in there very... By the way, of course the time's going to be really small. It's not like you notice the electrons traveling onto your screen. As far as you can tell, they get there instantly. They don't, but it's not like your brain can detect it. You get 2.44 times 10 to negative 9 seconds. Now, before you turn the page, stay on this page. What did we used to also then do? Well, now that you knew the time that was also the time it was being accelerated up for. So you could actually find how far it got accelerated up, the distance. You could actually, we used to actually assume we started in the middle 1 centimeter below. You could find how far it had traveled here, and you could actually calculate the angle theta of deflection. We used to do that. That used to be a Physics 12 question. It's been dropped from the curriculum. Also because TVs don't work this way anymore. What else? Well, the original black and white TVs, for this cathode ray, this electron gun, they had to warm up. This took a while, so that's why when you turned the TV on, there was as much as a 60-second delay while it warmed up. People don't like that. So the modern TVs stay on permanently. They shut the screen off, but a lot of the circuitry is still up and active. And what that means, Jake, is if you're ever taking apart a TV, because you're a nerd, you need to let that TV sit for about 3 months unplugged, because the way they stay on permanently, they use what's called a capacitor. They store charge enough to kill you, and it can be unplugged, and that charge will still be stored. Now, it will slowly bleed away if you unplug the TV. If you are playing with a TV and you want to take one apart, go ahead, but leave it unplugged for 3 or 4 months before you start mucking around with it. Number 1, number 2, number 3. Number 4 is the same as number 3, but it's a proton. I'm going to assume that you could do it for a proton the same as for an electron. It's just going to be a different mass. Same charge, though. Five is good. I nuked 6 because that was actually asking you to find an angle theta. 7 and 8 are good. $11 is a good because one's a point charge. Yeah, one's a point charge. One's not. Actually, you know what? I'm going to nuke 11 because I'm going to be giving you a big review of everything here. Let me see. I think what I'm going to do is 1, 2, 3, 5, 7, and 8 are good for this lesson, and I'm also giving you the great big review. Let me hand that out.